Hello everyone. Today's note starts at 268. That's the page number. But there's several clicker questions first. So please complete them on Canvas first. And right after that, there's a summary part for the parts that we covered. And again, these are really important to go through. So I'm just gonna briefly talk about these. In some problems, we may simply trade energy back and forth between accounts without any energy additions or removals. So you don't really need a force to kind of consume all the energy you have or anything like that. It could be just simply between energies, the transfer. And when work is positive, energy is added to the system. The energy can go into one or more of the accounts. They are on the left side in the conservation of energy equation. The first term is delta K, kinetic energy, delta U is potential energy, and delta I is internal energy. Again, work is kind of a way to add or take away energy from the system. So we can either add energy, or when work is negative, energy is removed from the system. This energy can be removed from one or two more accounts as similar to adding the work or adding the energy in the system. And friction and drag transfer useful energy from into thermal energy. So if you have friction or drag force, again, you can find the work done by those forces, or you can keep them as the change in internal energy, because they change the temperature. So we can keep them as kind of delta change in delta I, and we did specify the friction one separated from the general delta I in this past concept, but you can also think that in terms of drag force as well. Okay, so that's another piece, that delta I term can be used for drag force as well if we have drag force in the problem. Next is the supplemental examples. Again, these are the solutions are given. Please check these good problems here for practice. And again, the yellow box, that means that's the end of the chapter. So we finished chapter 8. And here we really focused on conservation of energy. This is very important for really most of you for your future careers, and because also it has the second law and the fourth and work done. This is a very important concept, so I hope that it is clear, and we are going to now move on to more sophisticated problems, okay, because there's some types that we still can't solve, and before solving those we need to understand how to deal with them, and by using what we already know. So we will figure that out first. So first of all, this is chapter 9. It's distributed mass. Some of the things in this chapter I'm planning to skip because chapters 10 and 11 is much more important for your engineering career. So I want to emphasize on those more. And again, I'm still working on eliminating some of the things that are not as important. Okay, just keep that in mind. I'm not exactly following the schedule, but so far we are pretty much similar with what we have on the schedule. Okay, so for the distributed mass, so far we've looked at the objects that can be considered as points or particles. Remember, that was one of the first assumptions we made. We're dealing with particles, and that means the entire object moves in the same direction and same speed, right? You're looking for any points on the object, and if any point on the object has the same direction and same speed, then you can say that that object can be assumed as a particle or a point. And we also looked at isolated single objects that do not really interact. So it's like, okay, we have normal force and friction force, but there's not much other interaction. So in this chapter, what we want to do is to expand Newton's laws and energy conservation to include also the distributed objects. And we would like to expand laws to cover several objects interacting, like collisions. And we will, meanwhile, we will also introduce the concept of momentum. So we're going to talk about linear momentum first, because we are not in rotational part yet. So we are going to understand what momentum is, linear momentum is, and later on, it's going to be a very important topic, which is angular momentum. So it kind of builds up on this. And we'll continue to use two laws, so it's second law and conservation of law. So we are not really making much changes in terms of equations. They may look different because of the symbols used and such, but they are based on those. So still, previous chapters are so important and everything really builds up. But again, the problems are going to be also much more sophisticated. Okay, but we are not introducing anything new, really, okay? So what are distributed masses? So in this first class, in the first semester, in the beginning of the first semester, in the first class, I did talk about this briefly, kind of give you the timeline and how we are going to look into the things. And I told you most of the class time, we can say the objects are assumed to be particles. Now this is changing. And what we're going to do in this chapter, we will only treat the center of mass, and we'll explain what that is, as the particle. Okay, so the center of mass acts like a particle, but the points on the object, they don't have the same direction or same speed necessarily, so the object itself doesn't act like a particle. Okay. But center of mass does. So if we understand how to find that and then kind of locate that point, then we can do what we've been doing for the other problems. So it's really straightforward. Okay, so let's try to understand what center of mass is. So if you consider a meter stick, for which the mass of the stick is in reality distributed over the entire object, if we envision dividing the meter stick into 1 centimeter pieces, then we would have like 100 of those pieces, right? Just kind of attached together. And each piece would have a mass which contributes to total mass of the meter stick. And if we define the center of mass, which is also called as center of gravity, as the point at which we can consider all of the mass of the object to be located. It's also known as the balance point of the object. So if you have a meter stick, or if you have like some sort of cane, you can put your, and I will share the video with that. It's a really cool trick, physics trick. You can put your index fingers on each side of the stick at the bottom. So you're just like kind of holding the stick with your 2 index fingers, okay, and nothing else is touching the stick, and kind of hold it horizontally. But you're not really holding it, it's just the stick is lying on your 2 index fingers, okay, on each side of the ends. And then bring your index fingers together and meet at some point. And what you're going to see is when you bring your fingers together, you're going to find out where the center of mass point is. So if it's a meter stick, and if it is nicely distributed, so it's like the same distribution of mass in everywhere, we're going to call that as homogeneous material. Then you would figure out that the center of mass is at the center, right in the middle point. But sometimes you have irregular shapes, and then it's not going to be like that. Like if you have a cane, you'll find out that it's not going to be the center point. It's like a nice trick to figure it out. And I will share the video. So here, CM stands for center of mass. Again, W is all the weight forces. We had several of them. In this case, we had 100 of those weight forces, but this W is the total weight. So as if entire meter stick is condensed at that single point at the center and has a mass or the weight of W. Okay, That's the total weight. So the equations that we have developed so far really apply to center of mass of the object. In a projectile motion problem, it is the position and velocity of the center of mass that we can determine. So instead of, if this was a meter stick and then we had a problem, we could still use what we know to figure out the position and velocity of the center of mass point. But we can't say, using whatever we have, like the equations we used, we cannot say what is the position or velocity of this point is, okay? So it only is applicable to center of mass of the object. And if you consider a figure, this is from Wiley Plus, or Wiley textbook. If we throw a bat, the bat's center of mass will trace out a parabola. So if you look at those black dots and then the purple dashed lines, that's a perfect parabola, because that's the center of mass. And even though you are throwing the bat so that it spins, that point stays in the path of parabola. And so that means we can still use the projectile motion equations, the constant acceleration motion equations for that center of mass point, the point that's shown with the black dot, okay? And we can predict where the center of mass of the bat will be at certain times, but not the handle or the tip of the bat or any other point but the center of mass point.